All right, we're going to change topics now. We've been talking differentiation for finding derivatives. We're going to do a new topic called integration, also known as anti-differentiation, which tells you something that it's the reverse. There's two types. Chapter 12 is the indefinite integration, and Chapter 13 is definite integration. Now, it doesn't mean that we're unsure of what we're doing here, but basically, but indefinite integration will yield a function. Definite integration will yield a number. So we're going to start on Chapter 12, Section 12.1. Well, let me write that here. That's where we are right now. But let's get some basic conceptual differences. This is where people get in trouble. When you're on the differentiation side, you're given the function. So I have here a revenue function. And you might be asked to find the marginal revenue, which, as we know, or you will see it written as MR. Now we know that the marginal revenue is the derivative of the revenue function with respect to the independent variable x. We can call that R prime x, and we can say that is 300 minus 0.3x squared. Notice I started with the function and I went to the derivative. Now I can do anything I want with this derivative. I can set it equal to 0. I can find the critical values of x. I could set it into the second derivative, see if that's max or min. But that's not the point right now. The point is, what's the difference? If I'm dealing with integration, somehow, some way, I know the marginal revenue. It's given me. Now, what is the marginal revenue? Well, the marginal revenue is the first derivative, or dr dx, and what do I want to find? I want to find the original function. So somehow, some way, I want to get from here to here. 300x minus 0.1 x third plus 100. In order to get from here to here, we do a process called integration. What do we do to get from here to here? We use differentiation. Sorry, it's not so clear. I should have left some space here. But we'll put the marginal revenue here. So what's the process we use to get from here to here? We use differentiation. Or differentiation. I think I missed a few words, but you know what I mean. Okay, changing the English language as he goes. Now, we use differentiation to go from the function, okay, the revenue function. What was that? 0.1 x third. Okay, to the marginal revenue, or the derivative, first derivative. Now somehow we're given the first derivative, and we want to step backwards to get the revenue function, which really models how the firm operates in terms of producing and sales. So the first step we're going to do is the definite integral, and the indefinite integral. That's what 12.1 is. So the first thing we're going to do is going to use 12.1. We're going to talk about the indefinite. So the indefinite integral is called indefinite integration. So that's your basic difference. So if you see a problem and they give you the revenue and they ask for the derivative or the marginal revenue, you do what we've done before. If you're given the derivative or the marginal revenue, you have to go through some antics to get back to the original function. So let's see, take an example and figure out what's going on. All right, let me put this down here. Marginal revenue equals 300. Okay. I know.
Bishop Sheen would sometimes talk about his angel that would come and erase the board he wasn't using.
Yeah, they'd have people doing it, yeah. That was great. Okay, so I'm going to work on this function, but first I'm going to take some simple functions. Although this is quite a simple function, but I'm going to start with just problems with only one term. So, first of all, so let's say we want to find the function given the following. F prime x equals 3x squared. Well, step one, when you're starting out, rewrite this lies this way. In other words, we're not using a shorthand, we're using what we're actually doing. Step two, multiply both sides of the equation by dx. So I get here df equals 3x squared dx. So what I want to find is f. In order to do that, I'm going to use integration. And I'm going to put an integral sign, which is almost looks like an S. So this equals the integral sign. Doesn't matter whether you're taking a definite or an indefinite integral using the same sign, just other things will happen. So you're going to have here integration of df is equal to 3x squared dx. So now let's see, what is the rule? The power rule. So rule number one of integration is the power rule of integration. It's basic, just like the power rule of the derivative, but not quite the same. So, if I'm given df equals the integral of ax to the n dx, then f is going to be equal to a x, add 1 to the power, and take the power, add 1, and put it in the denominator. And we got to add a constant, c. And you'll find out why we have to add that in a few minutes. So this is the rule. So I want to apply this rule to everything that I do. So what I'm going to do is I'm going to put this rule in the corner here, so I don't have to keep rewriting it. So if I'm given equals ax to the n dx, then f is going to be equal to a x n plus 1 divided by n plus 1 plus c. So I'm going to keep that there so I don't have to keep rewriting it. Now let's solve our problem. And let me rewrite the problem up here. I have integral df equal the integral of 3x squared dx. Okay. Well, we can erase this. And now I'm going to use my power rule. I'm going to say a equals 3 over here, n equals 2. So now what you want to do is you want to know that there's a special rule. And you can say number 2. The integral of any differential is what's on the right side. So the integral of dx would equal x. The integral of dr would equal r, etc.
Plus c.
Well, it's just the left side. Yeah, this is supposed to be a c, but I'm not going to introduce that.
Gotcha.
I know you're right, because they all lop into one.
That's true, yeah.
As I'll show.
They're on both sides of the
Yeah,
equation,
it
right?
just gets confusing. When I first taught that, and they said, "What are you?"
Gotcha.
Then I had to C1, C2. So we'll just leave this way. So the integral of df is going to be f, and this is going to be, according to that, 3 x 2 plus 1 over 2 plus 1, and now we add the constant. So the integral is going to be 3 divided by 3 x third plus c. Now that's what I wanted. I wanted my function, and we can say this is a function of x if you want. I didn't put the x there. All right, so my answer would be x third plus c. Now, of course, in most of the problems, the practical problems, we have to find c. But when we're just saying in the beginning, we're just going to use that as a c. Now, what was my original function here? I started out with, before, given f prime was equal to 3x squared, right? I came back to here. Now let's take the derivative of this. 3x squared, right? Well, that would be the derivative of this plus the derivative of this. And that's 3x squared plus 0. Why? Because the derivative of a constant is always 0. Unfortunately, the ease in doing that gives us a problem with here. Suppose this was a cost function, and this was variable costs, and that's fixed costs. Well, unless you determine what the fixed costs were, you're not going to determine what your total costs are, as an example. So therefore, we must find C. So let's just give a little bit more accounting for C, because everybody I remember when I first taught this, I didn't bother really dealing with C, and people said, I don't see that. Ha ha ha. All right, so anyway, just a few bad jokes just to keep things running. All right, so let's just take a few examples of why C is important. All right, so suppose I had 3 functions. Suppose.
Oh, we only have 30 seconds left, I just realized.
Okay, so we will suppose in a few seconds.